It's helpful when we start out the whole idea of AC, single phase, three phase, to understand the difference between scalars and phasors. And what is a phasor? And what does scalar mean? So, say what is scalar? What do I mean by that? Well, first of all, let's answer a quick thing here. What is energy conversion? What is electromagnetic, and I'm going to say electromechanical because it's also involved here, energy conversion? What is it? So from a very, very rough, cartoonish standpoint, what electromagnetic slash electromechanical energy conversion is this. In one way of thinking of it, you have mechanical energy, you start with mechanical energy, something that's moving, and that moving part is magnetic, and so essentially as you move it, you convert the mechanical energy into magnetic energy. And magnetic energy then, through various things that we're going to learn in this class, becomes electrical energy. Some of that energy is lost and some of it actually does useful things. So, how we bridge the gap here between these two here is through something called Lorentz force law. And how this gap gets bridged is through something that we would call Faraday's law, which is one of Maxwell's equations. So there's another way to look at electromechanical energy, and that's where we have electrical, I want to get pick the right color and pen here. You can also start with electrical energy. You can go the other direction. We can convert the electrical energy into magnetic energy. And the magnetic energy can then be used. We can go essentially the other direction and come up with mechanical energy. So you can go both directions. Again, and these laws, they apply in both ways, that bridge these gaps, right? And there's a number of laws that we're going to deal with in the magnetic domain that you're going to learn. So the one of these things, the top one, is really, we could call this generation, and this is actuation here. So you got generators, you got motors. Okay, so that's mechanical energy conversion. Now what we're going to focus on right now in module 1 is the electrical energy part, and it involves voltage and current. And so when we're going to talk about scalar versus phasor, it's really the form that the voltage or current is being represented as when we analyze it. That's what I want to try to clarify to you. So electrical energy is what? Basically, we use W here. It's the integral of the voltage, which is changing with time, multiplied times the current, integrating that with time, and that would be electrical energy. This is a W, not, in fact, I'm going to change my symbol here because it'll get confusing in a moment. WE. Power, electrical power, I'll say it's instantaneous power, is just volts times amps, right? Now this power here, if we are working with AC power as opposed to DC, we really need to think of it not in terms of P, but in terms of an S, which I'm going to call apparent power. Okay, so this is DC. This is AC. And in the AC world, your apparent power divides up into real power and reactive power. And so the real power does the work, and it also creates heat and loss. The reactive power just circulates, and it tends to make wires bigger, because if you have a lot of reactive power, you have to handle more current to get less work for the same amount of work. So usually reactive power is not a positive thing, but sometimes it helps you smooth and stabilize things. So it does have a positive aspect to it. It can smooth things out, and it can stabilize things for you. Now, the way I'm describing this is a time domain signal, and it's at any value of t, let's say t equals t prime, there is an SE prime at that time, and that instantaneous value of SE is your scalar. So when we're talking about scalars, we're talking about something that's happening with time, and we have basically sampled and captured that at that instant of time. So let's consider an example of this to try to understand just a little bit more about scalars. I'm going to show you here an x-axis. This is time, and a y-axis, and I'm going to draw the shape of a voltage that, let's say, is being applied from a DC power supply to a system. and we'll just say that this is a resistive load. Okay, so that's the voltage waveform. And if it was just a resistive load, then the current would follow the same shape. Before I go any further, I want to introduce briefly something that we are going to talk about in more detail in this class in the future, which is per unitization, which is helpful in this situation to use because we're going to be looking at two signals. One is in units of volts and one is in units of amp, and eventually we want to look at power, and I want to look at all of them on the same axis. So what we do in per unitization is we establish a base voltage. So there's a V base, and we would also establish a base current, I base. And so the voltage that we're operating at, that's shown by the blue curve here, would be V. And if I want to put everything on the same scale, I will put it on a per unit scale, which means that I will have this V PU. And so the V voltage divided by V base is the VPU, and the IPU, PU meaning per unit, is the current divided by I base. And so what we're showing here is V per unit and I per unit. Now the behavior we're seeing here, as far as these waveforms go, can really be divided into two parts. This part of the waveform is a transient behavior. This part here, everything is steadied out, it's reached its level and nothing's changed, so we tend to call that steady state. It's steady state behavior right there. And so at steady state, let's say V equals 100, and the current steady state level, let's say, ends up being at around 7 amps. If I were to establish the V base as 100 volts, then I would get, just as I'm showing here, V per unit at 1. And if I establish I base at 10 amps, then I per unit would be 0.7. And so that would line up with what I'm seeing right here. Okay, so cleaning things up, let's talk a little bit about scalar behavior. Scalar, like I said, would be the amplitude that's captured at any instant of time. So if I were to establish, let's say, T1, at that time period, the current and the voltage are going to be some level. So we're really describing here, this is V per unit as a function of time, and I per unit as a function of time. So VT1 would be about, maybe be 0.6, and I per unit T1 would be about 0.4. Now these are per unit. I just want to make sure that you understand that scalar, I could have measured these in volts. The scalar value could have been 60 volts or 4 amps in this case. It doesn't matter whether I'm per unit or real units. I'm just trying to show these on the same plot. I just want to make that clear. I could also do a power calculation at that point. So the power, the instantaneous power, per unitized of course, because these are both in per unit, at T1 would be V per unit at T1 times I per unit T1, and so that'd be 0.6 times 0.4 or 0.24 per unit. And I could take, let's say, another value right here in scalar at T2, and I'm at steady state there. So VPU at T2 is 1.0 and IPU at T2 is 0.7, and the per unit power at T2 ends up being 0.7 per unit. So as far as scalar goes, it really doesn't matter whether you're in a transient mode or you're in a steady state mode. And so really when you're doing calculations of, let's say, a magnetic system like you will in chapter 1, you're going to be doing a calculation at a given value of, let's say, current in a coil. That's a scalar point. And when we go into AC systems, the scalar values aren't very helpful to us, and that's really why I'm talking about this. And I want to make this, straighten some things out and make a few things clear. Now, what you could also have to emphasize this before I talk about the AC, and I can do this because I'm recording this, and I maybe have a little more time, okay? But let's say that this voltage here was being applied from a DC power supply to some other kind of a load, like let's say it was a purely capacitive load with a little bit of inductance in series with it. You would get a transient behavior that'd be very different. Your voltage would tend to get some ringing in it that might go for a while. So what you're seeing there is an AC component on top of the DC component, and the current might of course look very different if it was that kind of a load. So you're probably getting a big surge of current like this, and maybe there's a little bit of loss in that load, but it's mostly a LC load charging up a capacitor. It's like an inrush transient. So the per unit, the current changed, of course, because the load changed. The voltage at the steady state is the same, but there's this ripple on top of it. Now you could say you could sample or just look at all of the points sampled in this same region right here that we were calling steady state before, and you could average together a bunch of little points. Okay, so you could take all these little points right here and you could find a V per unit average, which I like to use this symbol here for average, and that would be the sum of from n equal 1 to however many points you took, let's say n points, of VPU T sub n divided by n. That's an average. And what the average will look like is it will be exactly the same level as we had here before. That would be your V per unit average. So there's some, when we're making measurements on signals, or if we're making measurements in the lab, like you'll see in our power lab, we're using instruments. Instruments do some processing, they do some filtering, they do some averaging on the signals that are being measured, and this is what you're looking at typically. So there's a difference between a scalar value and, let's say, what you're going to measure with a typical voltmeter, because the voltmeter is going to either average that, or it could do a root mean squared, an RMS, right? So what would that be, right? If you said I've got a V per unit RMS, what does that mean? I'm going to, its RMS means root mean square. So you square it, you take the average of the squares, and then to take the square root in that reverse order there. So the V per unit RMS equals the sum of n equal 1 to n V per unit Tn squared divided by n. Now you've got your averaging, and then you're going to take the square root of the whole thing, and you probably get a very similar number. If there's a little bit of AC content in here, it'll be a little bit higher, but it's going to be a flat number. It's going to be the same number over the whole period that I took the samples of. So what you have is you have scalars, you have averages, and you have RMS, different ways of looking at things. Okay, so let's talk about alternating current, or AC, quantities. I'm tempted to say signals, and because a lot of what you have learned in electrical engineering is at the signal level, but we're talking about power here. This is not a signal. These are real voltages and currents. That means they're more than 3 volts or 10 volts. We are still in the per unit, so we still have per unit quantities. If we do that, then we're saying that this blue line, that would be the V per unit. It's time varying, and it has an amplitude of 1.0, and this is the I per unit, time varying, and it's also 0.7. And so the amplitudes are now representing the steady state amplitude that we saw in the previous slide is representing the peak of a periodic waveform. We're also just going to constrain our discussion to the steady state. Now in the steady state of this, the amplitude, the peak amplitude on the top and the peak amplitude of the bottom are equal to each other. And this waveform has a period at which it repeats. So we'll say this point right here is t equals 0. So that's a point of reference, and everything to the left is, history, and everything to the right, is the real-time stuff that we see going on right in the today, right now, and in the future and beyond. Okay, we're looking at this on an oscilloscope, and it's going to look this way. So the peak will repeat when a period is completed, and I'm going to define that period as t. And we're talking about a resistive load in this case. So since we have a resistive load, the current IPU is proportional to VPU at all t. They're just different from each other by a scalar proportional value. Again, we could find scalar points along these curves. So we could say here's T1, and we can pick those points off. And we're going to get a number, and we could pick another point here. We could call that T2. And we're going to get another set of numbers that are different, but they're not going to be tremendously meaningful to us in this AC world. So we need to come up with something else we can use. And so what that is we've got two choices. We talked about them just in the past slide. We could use an average, or we could use the RMS. Well, when we do an average and an RMS, and we did it in the previous slide with the DC quantities, we just took some arbitrary number of points after it reached steady state. Here, if depending on what period of time we average over, we're going to get a different number. We want to get the same number all the time because this thing's not really changing. And so what we want to do is we want to take the average or the RMS over this period here. It's periodic, and when it repeats we would get the same average or RMS. So that's how we constrain our average or our RMS calculation. So cleaning things up again and looking at this same waveform, we can actually write an expression for VPU and IPU. And the VPU expression, it's sinusoidally varying, right? And if we look at this, is defined as time t equals 0, then we're going to encounter the peak when t equals 0. So that means that we're going to want to use a cosine. So the peak, we could be general and call this V peak. I'll just put a little subscript, it's per unit, times cosine, and we say cosine of what? Well, this is a periodically repeating waveform, So the frequency at which it repeats, we'll call, is F sub E. Electrical frequency, that's 1 over T, and that's in the units of hertz. And if what we know that a cosine is going to vary with an angle, so we have to make this angular. Essentially, there will be a period where everything repeats that corresponds to 2 pi, right? So the angular frequency is 2 times pi times Fe. So this is going to be omega E times T. And the I per unit is going to be equal to some peak current I peak per unit times the cosine of omega E T. And so obviously we've been talking about a resistive system. So we have it's applied across a resistor R. And so we would know that I peak equals V peak. Now that I'm showing this in real units, divided by the arm. So I peak in amperes is V peak in volts divided by R. Okay, so we have this established. We have these expressions. Now we are really trying to ask the question, do we want to do an average and we want to get one number to tell us what's going on, or do we want an RMS? So does an average make sense? Well, another way to think of an average would be, if I want to average over this period t, it would be, let's take the area under the curve that's above 0 and the area under the curve that's below 0, and sum those up, the areas, and divide them by t. That's an average. Or mathematically, what is an average? V pu of t averaged, in this case, would be the 1 over t integral from 0 to t of V pu t dt. So that's mathematically the same thing as saying add up the areas under the curve around 0 and then divide them by t. Well, obviously, because these areas are equal and this positive area equals that negative area, it's going to be 0. So average is not a good choice to use. So let's talk about whether RMS makes sense. And I've kind of cleaned things up and I'm amplifying things a little bit, and we're going to focus on the voltage first. The first thing I want to do is, though, let's talk about the period. Okay, so the period of this waveform over which it repeats every period, that's t. We've already established that the frequency associated with the sine wave or cosine wave has an angular frequency of equal to 2 pi Fe, or that's same as saying 2 pi over t. And I'm really distinguishing between frequency and angular frequency. What angular frequency has the units of radians per second. So there's a an angular distance of 2 pi between these points. We know that's exactly how this trigonometric functions work. They are periodic according to 2 pi being inside of these parentheses right here, right? When you put 2 pi in there, you're going to get same as it's going to be 1. It's the same as saying cosine of 0. So we could instead, let's just not use this and let's use a period of 2 pi. That's going to make our math easier for sure. And if we do that, then we can also change what this axis is. So that axis is really the same thing as saying omega e times t, and that is an angle. And we could also say that that angle is, we'll just call it theta e. So that's an even easier way to write this, and we can take t out of it. Now instead of the t and the 2 pi in these two reference frames they have the same meaning. And so if we were to say do an average of something, we could say, if we're doing it in time, we could do it with 1 over t. But if we're doing it with position, we can say 1 over 2 pi. So that makes things a lot easier for us. Okay, so now let's look at the root mean squared. Sometimes I might write it as capital, sometimes as lowercase. It doesn't have any meaning here. Now what I'm going to do is write the function for the RMS. We're going to square this function first. Now it's quite a simple function, cosine of theta e, because I'm doing it in terms of the angle. And this is a per unit peak value. And I'm going to square this whole thing here. Step 1 of the root mean square. Then I'm going to take the average of it, integrate from 0 to 2 pi, integrating it over theta, 1 over 2 pi. And then the square root. So you would take the square root of this entire thing. Now we can clean things up a little more here, because we know that V peak per unit is equal to 1. So just for the purpose of illustration of an RMS, we will just use the voltage because the peak is 1, and we know that V peak per unit squared is also equal to 1. So I can simplify this equation a little more. And we know that there's a trigonometric function for cosine squared of theta. Well, that makes things easier to deal with. So we would be plugging this into here. Now we know that integrating, taking an average, not integrating, but taking an average of a periodic function over a period, which is 2 pi, or even if it's 2 theta, that would be 2 periods. It's the same thing as taking an integral over 2 cycles of this waveform. It's going to be 0. So any part of this is really, when we take the average of it, it's going to end up being 0. So all we end up with is this. So working out the integral, that's going to simply be theta over 2 evaluated, taking the difference between it at 2 pi and at 0, and then this whole thing here, of course, is multiplied times 1 over 2 pi. So, of course, what you get, and I know that this has been a little bit of a duh moment, 1 over 2, right? 1 over square root of 2. So the RMS of any sine wave, and this is going to be equal to V peak per unit, since we were using the per unit here, divided by square root of 2. Or if we were using voltages, the V RMS is equal to V peak divided by root 2. So we've established that the same thing will happen with the current. The I RMS is going to be I peak divided by root 2. So RMS quantities are the quantity that we will be working with when we work with AC signals, AC quantities like voltages and currents. Okay, so now that we've established the difference between a scalar and an RMS with periodic waveforms, let's talk about some useful ways of looking at AC systems. So first of all, we've established that, and I'm going to now go away from this per unit scheme that I was using. We'll just call this is voltage V, and this is current I. And the voltage V is a cosine right now, so it's V peak cosine of theta E. We've established that theta E is equal to omega E times T. Another way to look at this, by the way, it's an angle or a position, angular position, and this is an angular frequency or speed. So you could also say that theta E is equal to the integral of omega E with time to get the same result. Okay, so I digress a little bit there, but I've got I peak of cosine theta E as well. Now I've also established that VRMS equals V peak divided by square root of 2, and I RMS equals I peak divided by square root of 2. Now, knowing that, I could, in this class, we're only going to talk about AC systems operating in the steady state. And when you go into the lab and you make voltage and current measurements on AC, you will be measuring an RMS. In fact, all meter measurements nowadays, like fluke meters and things like that, are RMS or true RMS readings, which is that it's mathematical RMS, just the way I explained it with the DC system.